So let's get started. We're going to play online convex optimization game for, I guess, basically all of this session. So let's define what that is. We're going to play this game in several rounds. In each round, a learning algorithm is going to pick some vector WT in a convex set W. And then some evil adversary is going to come up with a convex loss function, LT, and the learner suffers loss, LT of WT. And the objective is to minimize this thing called regret, which is the total loss suffered by the learner minus the loss suffered at some comparison point. You can sort of immediately, upper bound the regrets due to convexity as a linearized regret, where you take the subgradient or a gradient of the loss functions at the particular point you tried and look at this linearized regret. And because linear functions are sort of also convex, we're just going to immediately consider only the linear case, which is pretty standard. Something that's a little bit less common is I'm going to consider regret as a function of u. Often, if you take the first class on online learning, you'll see regret as the maximum of this function over all u and w. But that is always infinity when you look at an unconstrained space w, which is unuseful for us. So we're going to think of bounding this regret uniformly by some other function of u. All right. So what can we do in this setting? Well, it's pretty well known that you cannot do something that guarantees better than just u times Lmax times square root of t, where Lmax is the maximum Lipschitz constant or the maximum gradient norm that you see over the course of your optimization game. And by the way, for all of this talk, I'm going to consider only the 2 norm. Some of the results extend, but don't worry about it for now. And this lower bound can be achieved easily by gradient descent with just a constant step size, where eta is, norm of u divided by Lmax divided by root t. So it seems like problem solved, we should all go home or something. But of course, the problem is a little more complicated than that because we don't really know how to set eta. Nobody's going to tell you ahead of time, hey, this is what u is, this is what Lmax is, unless you happen to know something already about the particular problem you're trying to solve. So there's this hyperparameter tuning problem that comes up where people in practice just basically make a guess for what eta is and hope to God that they got it right. Right? So we'd like to come up with an algorithm that can automatically adapt to these unknown parameters. Well, let's try to go just halfway. What if we only know one of the 2 things, u or Lmax? And this is also fairly well studied. If you don't know Lmax perhaps, but you do know u, you can run basically attograd, and that'll get up to constants at least actually the exact same regret as you would have gotten if you knew all the information. So things are looking really good. What if you didn't know u, but you do know Lmax? Then the updates actually become weird and complicated. But you can still show that you can get regret that's the optimal u times Lmax times root t times this extra square root of a log term. And it turns out that this square root of a log is unimprovable. So in some sense, not knowing u, looking in an unconstrained setting, is fundamentally harder than the other setting. On the other hand, square root of a log is not that scary, right? So fundamentally, you should expect that not knowing half the information is basically as good as knowing all of the information, which is good news. You might think, well, maybe if I knew no information, I would still be able to do just as well. Unfortunately, you're out of luck. So about a year ago, I showed that if you don't know u or Lmax, the problem becomes impossibly hard. And it's impossible to achieve, even up to log factors, this ideal regret bound. In this paper, we're going to significantly improve this lower bound by showing there's actually a frontier of lower bounds that trade off between this ideal regret term and some exponential penalty. And then further, we're going to show that, in some sense, this entire frontier is tight. By designing for any point on this lower bound frontier, I will design an algorithm that can guarantee regret matching that lower bound. And the way we're going to do this is by doing a whole bunch of really ugly algebra, which I will not show you and is swept under the rug into the appendices, and then surfacing from that a few relatively nice-looking theorems that allow fairly quick and easy design of algorithms for this information-free setting. I should make clear, we started with some idea that we'd like to have a hyperparameter-free optimization algorithm. But really, we're not going to get that, right? This algorithm really requires you to pick a particular point on this trade-off curve, which is, in some sense, a hyperparameter that the algorithm designer has to pick. But what's fundamentally different about this is that it's really a free choice. It's not like that learning rate eta, where there's sort of an actually correct value that depends on some unknown problem parameters that if you pick wrong is your asymptotics and your regret bound are totally wrong. Any particular hyperparameter you pick, I can guarantee you what the asymptotics are going to be. All right, so we're going to talk about the lower bound first. Before I actually describe it to you, I'm going to describe briefly how the adversarial sequence that gets you the lower bound works. And it's actually relatively straightforward, if a little bit pathological. We're going to play a one-dimensional online optimization game. And what the adversary does is it just keeps giving the learner the gradient -1, just -1, -1, -1. And this forces the algorithm to really, seriously give credence to the possibility that it will never see anything other than -1. So that actually the biggest gradient is just 1. And this, in turn, makes the algorithm necessarily explore space to a certain degree of aggressiveness. It has to, get far away from the origin because maybe it'll never see anything bigger than -1. And then, of course, the adversary immediately turns around as soon as the learner has explored sufficiently and says, guess what? Actually, the biggest gradient is like t or something. And that totally screws up the learner because it's now explored too aggressively. All right? So this, in an adversarial setting, really makes it impossible to get good regret, but it also is very pathological in the sense that the gradients have grown extremely fast during this procedure. And that's reflected in the lower bound. So I'm going to show it. Be prepared. It's like kind of a complicated formula, even though I've already simplified it some. So for now, I'd like you to ignore all this colored jargon and just look at this term, which is the ideal bound, plus this other term, which is information-free penalty, which is exponential. And the quantity it's exponential in is this ratio, LT, divided by LT minus 1. So I defined LT to be the maximum gradient that the algorithm has seen at time t. So the ratio LT over LT minus 1 is really quantifying the rate at which the gradients are growing over time, which, as you recall from that adversarial sequence, is actually pretty high in that case. All right, so now let's look at these colored terms. There are two trade-off parameters, k and gamma. The way this works is the adversary is going to pick k and gamma, sort of free choice by the adversary ahead of time, and then it can choose its point at which it decides to surprise the learner and the degree to which it decides to make that new gradient really high in such a way that the ideal bound component of the regret is scaled up by a factor of k and by a log to the gamma power. In turn, by making this k and gamma bigger, we've increased the contribution from this ideal regret bound, and so we decrease actually quite fast the exponential term. All right? So this is kind of depressing, right? Exponential penalties make it seem like all hope is lost, but people can and do solve this problem in some sort of practical sense a lot of the time. So there is actually hope in practice. And the idea is that maybe this exponential term is actually small because the gradients aren't growing that fast. And in fact, you might expect in a stochastic setting, that's exactly what you should see, because the first gradient you look at is probably the biggest gradient because you're furthest away from the optimization, from the optimal point. So it really would be valuable, in fact, to design algorithms that do actually meet this bound. That's what we're going to do next. The algorithms we consider are all going to be follow the regularized leader algorithms, or FTRL. This is a well-known and very classic way to design online learning algorithms. I'm just going to briefly summarize the idea, which is at each step you choose some regularization function. It's often like w squared, but it won't be for our cases. And it's often given by some multiple of some base regularizer. And then at the tth step, you set the tth the wt plus 1 to be the thing that minimizes your regularization function plus the sum of all the gradients that you've seen up until now. And there's been a lot of study into this, but one of the main results is that if your base regularizer is strongly convex, then the regrets can be bounded by some contribution from the final regularizer plus some sort of bookkeeping term that grows over time. Now, this is a sort of appealing form of a regret bound because it sort of maps onto the lower bound that we have. You can think of this final regularizer as maybe looking like u times log gamma of u, and this bookkeeping term as sort of looking like the exponential penalty. Okay? Unfortunately, that's actually not going to work out for us because if something is strongly convex, it has to be bigger than a quadratic. And u times log gamma is never bigger than any quadratics. So we can't just blindly apply this type of theorem to immediately get the regret bound that we'd like to have. We're going to do something a little bit more general. And I'm just going to sketch some of the ideas behind how you do this. The first observation is that you don't actually need the regularizer psi to be really strongly convex. It suffices to consider just a ball that contains, the comparison point u and all the points that have actually been explored during the operation of the algorithm. That's sort of an effective domain. And if the regularizer is strongly convex on that domain, then you can still apply this theorem. So the regularizer W times log W effectively, you can add the plus ones to make it convex, is actually 1 over B strongly convex, and then you can just get this type of bound. This is still not good enough though, because we don't really know what B is. And just doing a sort of naive bound on how big the WTs are going to get over the course of your algorithm, you'll see that it's probably something like e to the square root of t, which is horrible, right? Square root of LT over LT minus 1, maybe I can handle. Square root of t is like off the charts bad. So we need to do something significantly more clever. I'm not going to go into how that works, but basically the idea is that if you choose the regularizers according to some particular schedule, then you can actually show that whenever WT is really big, in fact bigger than this LT over LT minus 1, then actually the bookkeeping term doesn't increase at all. And so you can control that setting and say that effectively in some sense you can think of B as just being equal to this e to the LT over LT minus 1. Okay? I'm not going to go into the details of how you do that. I'm going to describe, though, the particular ways you choose the regularizers. So here's how that happens. A user will pick some base regularizer, which will have to be something like strongly convex, which I'll get to in a minute. And then they'll pick a value k. So the regularizer should hopefully look like W times log to the gamma of W. And that's going to set the gamma part of the lower bound. And the k is some user-specified constant that sets the k part of the lower bound. This is the part where you choose a point on the lower bound frontier. And then we have a relatively technical-looking procedure for choosing some numbers eta t and at. You can think of 1 over eta t as being, roughly speaking, L times square root of t, and at as being, roughly speaking, t, but they're both carefully designed to be as small as I can make them so that the bounds still work. And then you set the regularizers to be this particular formula. Notice it's a little different than just scaling the base regularizer by a constant. We're actually scaling the argument inside here too, which has some technical consequences but is not particularly different. Okay, so I mentioned that you need to have something kind of like strong convexity for the base regularizer psi, so I'm going to describe those conditions here. It's a little bit more complicated, but it's still, like strong convexity, fairly easy to verify. So if you take any 3 times differentiable function f that is 0 at 0, this part's not really necessary, but I don't like carrying constants around too much, so we impose this. It's increasing, it's convex, but it's sort of getting less convex as you move out to infinity. But it's not getting less convex too fast, so we want f times f double prime to actually go to infinity. All right? These are sort of, this last condition is really kind of technical, but we'll get to it in a minute. Now, we define psi, the base regularizer, to be f applied to the absolute value of w. And we call this type of psi an adaptive regularizer, because adaptive is a cool word, and we're going to use it to make algorithms that adapt these unknown parameters. So we also need this function h, which is f times f double prime. And I really defined h only so that I could talk about h inverse, which is going to show up in our analysis. And this is really why we needed this condition 5, is because h might not actually be invertible, but under this condition that this limit goes to infinity, we can define a kind of pseudo-inverse, which suffices for all the purposes that we're going to need. And you should verify, maybe not right now if you don't want to, but like pretty quickly you can see that like a strongly convex regularizer like w squared is actually going to satisfy all these conditions. So you could use this to reprove that original bound, but that would be a lot more work than you needed to do. What's more interesting to us is that the function x plus 1 times log x plus 1 minus x, which you should think of as just being x times log x, is satisfying all those conditions. And so you can construct an adaptive regularizer based upon this function. And the h function is exponential. So that should maybe pique your interest a little bit. The h inverse is going to show up in that bookkeeping term, and that's going to give us the exponential regret bound that we were looking for. So without further ado, or I guess with just this much further ado, I'm going to describe the regret bound. So here is restated the standard bound for a strongly convex psi, where it was the final regularizer plus some kind of bookkeeping term that usually you can make look like that. In contrast, with an adaptive regularizer psi and those particular choices of eta t and at that I described, you can get something like this. So this is, again, just the final regularizer with some asymptotics particularly factored out. And this is the bookkeeping term, which is now in terms of h inverse. So it's a little bit more complicated. I'm not going to do the math in detail, but I'm going to throw up some equations that tell you that I did it in detail, and tell you that if the base regularizer is this u times log u, then you can show that this final regularizer is in fact the ideal term that we were looking for. And when h inverse is x sub x, which it is when this is the base regularizer, then this second term in fact matches the bookkeeping term that we were looking for. Or the bookkeeping term in fact matches the exponential penalty that we were looking for. So that's great. That means that at least for gamma is equal to 1, we actually can solve this problem for any particular k that we liked. But we want to do it for any gamma from 1/2 to 1. So we have to go a little bit further. And that's actually pretty easy to do, because checking whether something is an adaptive regularizer just involves calculating like 3 derivatives. And anybody can calculate derivatives. So I'm going to define this function, which makes it particularly easy to calculate the derivative, because the first derivative is already calculated for me, as the antiderivative of log to the gamma. And you can sort of immediately see that if this function is going to have the appropriate x times log to the gamma of x asymptotics. And without too much ado, you can actually compute the third derivative and see that, in fact, satisfies all the desired conditions. So using these regularizers, we can match the lower bound for any particular k in gamma. Now, I know I went through that relatively quickly, so I'm just going to restate what the user would actually code up in a computer, because nobody writes down integrals inside of a computer. And it's actually pretty simple. I also give it a name. I call it FreeRex, because branding is the most important part of algorithm design. And the way it works is the user chooses gamma and k. These are the lower bound parameters. And in your head, while you're coding, you think about, oh, I'm going to have this f, and I'm going to run FTRL. But what you actually write on the computer is this simple formula. I'm not going to read it to you, but you can probably convince yourself that it takes a couple lines to write, and the space and time complexity of this algorithm is the same as baseline gradient descent. So using this, you can easily match any point on the frontier. I'll just sum up. So we showed that in the information-free setting, it's actually impossible to achieve the ideal regret bound that you'd like to achieve. Instead, there's this two-dimensional frontier of lower bounds that are each sort of incomparable with each other and trade off between this ideal regret term and exponential penalty. We showed that finding these adaptive regularizers, which is some kind of generalization of strong convexity, is enough to design algorithms that get sort of non-trivial guarantees in the information-free setting. And we can use this machinery to, relatively trivially match any point on the regret frontier. So that's it. Thank you.
Right. Questions?
Can these results be reversed into the simpler, expert setting?
So the question was, can we apply this to the experts or hedge setting? So in the expert setting, you already have a bound on your comparison point u sort of ahead of time, and so it's a little bit somewhat easier. I haven't thought particularly about doing this. There are some sort of reductions that generally take online convex optimization algorithms to expert settings, but I think probably other approaches like Squint or something might outperform this type of procedure.
One more?
Yeah, I'm totally curious that your regularizer was actually entropic. So you had sort of the basic setup was gradient descent, and then you use the regularizer as entropic, which would assume that it's close to edge or exponentiated gradient.
Yeah, so there is a strong relationship between this and exponentiated gradient. You can think of this as like there was a paper several years ago called dimension-free exponentiated gradient. This is very similar to that. But really, the way I picked that regularizer was I looked at the lower bound and I said, that's what I want the regularizer to be, right? So I haven't really thought too much about, I suppose, the proper connection in terms of the expert setting, but that is definitely an area for future research. Yeah.
All right, let's thank Ashok again.